And we're just going to talk about 1 through 4 just to make sure we have the materials down here, the concepts down. So this is OCE S4. The situation, of course, prior to the 2016 election, Remington Research Group and Axiom Strategies conducted a poll in Wisconsin to find the voting preferences of likely voters. Survey was conducted on November 1st and 2nd, 2016, among 2,720 likely general election voters. Survey found that 49% supported Hillary Clinton, and 41% supported Donald Trump. The margin of error was plus or minus 1.88 percentage points, and that's at 95% confidence. Number 1 right now. So problem number 1 is asking us identify the sample size and sample statistics in this study. So the sample size is what here? How many people were actually surveyed or actually gave responses? Perfect. 2,720 voters. And actually the term likely voters, because some of them may have had something come up and didn't actually vote. Some people that said they weren't going to vote may have actually made it to the polls and voted. So that's our sample size. Sample statistic. Remember, a statistic is something that describes the sample. There are 2 statistics here. Can you tell me what they are? Perfect. Those are our sample statistics. And of course, included with that, we should include there is that margin of error. Now, the next step, question 2, identify population parameters, or sort of population parameters of interest in this study. So we're not actually going to put a number on the population parameter, but what is it that they're actually trying to find? What is it they're trying to learn? Yeah, who people are going to vote for, right? Who voters will vote for, I should say. So that is the parameter of interest here is they're trying to predict the winner of this coming election. So the parameter is who they're going to vote for, what the votes are going to end up being. Number 3, use this information above to create the interval estimate. Now, we talked a little bit about interval estimates. Remember, these numbers up here, the 49% for Clinton and 41% for Trump, are called point estimates. Do you remember how we turn those into interval estimates? Okay. We use that margin of error, the 1.88%. So for Clinton, it's 49%. We subtract 1.88% to get the lower end, and we add it to get the higher end. So when we subtract it, we get 47.12. If we add it, 49 plus 1.88 is 50.88. And the technical way to write that is just how I expressed it here with parentheses around it. That is what's called a confidence interval. It goes from 47.12 to 50.88%. For Trump, how would we find his interval? Perfect. 41 minus 1.88 and 41 plus 1.88. And we get that range from 39.12 to 42.88. Now, looking at these intervals, we look at them and we see that the bottom end for Clinton is 47.12. The top end for Trump is 42.88. What is that telling us about what we should expect for the results of that election to be? Yeah, since the two intervals don't overlap, what this is saying is based on this survey, at 95% confidence, Clinton should win. So let's go back and revisit that term 95% confidence. What that is telling us is 95% of these intervals, if we repeated this survey over and over again, 95% of the time, the interval for Clinton would contain the true percentage of people that's going to vote for Clinton. And 95% of the time, the interval for Trump will contain the true percentage of people that will vote for Trump. So if that's the case, then at 95% confidence, these intervals won't overlap, and we should be able to relatively safely predict that Clinton is going to win. So now we have this confidence interval for the sample for each. And we're using that, and the purpose of that is an estimate. That's an interval estimate. Technically, interval estimates for the population proportions. Technically, we won't know the actual population proportion until after the election, which are actually very fortunate in this type of case because at some point we will actually know the population proportion. In most statistical applications, we will never know the true population proportion. So we won't ever really know how accurate our prediction is. At least in this one, we know it at some point. But anyway, the purpose of doing these samples is trying to estimate that population proportion and predict what it's going to be. And that's why we use the confidence intervals. Now, the one thing we haven't gone over is how do we get this margin of error of 1.88? And that comes from the confidence level. And one of the things we didn't get to last week is the confidence level goes down, that margin of error would get smaller. They're directly related. We did talk slightly about the margin of error and sample size. If the sample size gets larger, the margin of error gets smaller, right? We saw that when we took those samples out of that population that we had programmed into Excel. We sorted them out, and we noticed that when we were doing a sample size of 15, our sample proportion was really close to the same every time. When we dropped down to a sample size of 10, well, it jumped all over the place. So the larger the sample is, the less error, the less the margin of error will be in the results of that sample. And then the level of confidence, this is a direct relationship. The larger the level of confidence is, the larger the margin of error is going to be. So at a 90% confidence, we will have a smaller margin of error than we would at 95% confidence. Because that confidence level gets larger, the margin of error would have to get larger with it. So again, the purpose of taking these samples is trying to make a statement about the population. So the last thing we're asked to do in number 4 here is use this information to create an estimate for the proportion, the population proportion for the voters who will vote for Trump. So the way we would do that is whenever we make a statement about a population parameter, we do have to state a level of confidence. So we'll say at 95% confidence, the percent of voters who will vote for Trump is between 39.12% and 42.88%. That turned out to not be quite correct in the election, but it was, the result of that study. We talked a little bit about how even though the statistics are done great, the 95% confidence did give that plus or minus 1.88%. It still may not be in that interval because there might be other things about the survey that went wrong. And anytime there's a political survey, of course, there's always changing opinions. I don't know if you paid much attention to the election in 2016, but just a couple of days before the election, there was a bunch of information leaked about one candidate that made them look really bad, which may have changed those results right up to the minutes and hours before the election started. So, of course, any sort of political survey has that qualification. So technically, we should state that this was on November 1st. So on November 1st, which is when that survey was done, we are 95% confident that between 39.12 and 42.88% of voters plan on voting for Trump. There may have been a lot of things that happened between November 1st and the actual election day that changed that. Okay, any questions? Okay, so I want to take a peek then at our P&L. Yes, Sam. Yep, I actually have it paper and pencil if you prefer to do it in class. Okay. Okay. You should be able to. I will make sure I go through and double check. Make sure everything's set up perfect for you. Otherwise, I will, if nothing else, I can send it up there. I've got to verify that the paper and pencil copy that I have is exactly the same as the online one. And if there's any issues, the very worst that could happen is I send the test up there and you can take it Monday afternoon before you leave. but I will verify to make sure that the online version and the paper and pencil version are the same. Then you should be able to just take it online. It'd work out better to let you have that extra day or so to study. Oh, sure. The 25th or 26th? Okay. So not much break for you, huh? Okay, in the P&L, we had, they're talking about global warming. And they gave us this graph here on global warming. And actually, this one, what they're really talking about here is they're talking about the Arctic ice caps, the Arctic sea ice caps, and they call it the ice extent. In order to keep it consistent, because it does shrink and grow every year considerably through the seasons, it's usually at its smallest in late July, early August, depending on the temperature, depending on how the weather's going. So they measured it in July every year. And what they're showing here, starting in 1979 and going to 2015, it appears as though that ice extent, the size of the ice caps, is shrinking. So one of the things they wanted us to do in our P&L was to create a model for that. And what they recommended doing was picking points somewhere in that data and just kind of drawing a line through it. So it all depends on what points you pick. But you can tell, if you're drawing a line, your line would look something like this going through those points. So I might pick the value for 1981. And let's say the value for 2013. Those seem to be relatively middle of the road values. So in 1981, it's 10.7. That's just millions of square kilometers. So that's 10.7 million square kilometers of ice cap. In 2013, it looks like it's 8.5 million square kilometers of ice cap. So if you remember how to make a model out of that, remember our linear model has two pieces to it. It's y equals that first piece is the starting point, which is your y-intercept, plus your second piece then is the slope times your x variable. In this case, the x variable would be years from 1997. Or 1979, not 97. So let's take a look here at finding that information. The starting point is just going to be the value in 1979. So what is the value in 1979? $10.5 million. Now that's going to be a little off because that line we sketched in actually hits above that slightly. But we can, this is just an approximation, so we can use that 10.5 million as an approximation. So it's 10.5 million plus or minus whatever our slope comes out to be. Now remember, slope is your change in y over your change in the x variable. So our change in y we went from 10.7 to 8.5. So it's actually 8.5 minus 10.7, which is a negative 2.2. Our change in X, well, we went from 1981 to 2013. How many years is that? Looks like 32 years. So it's a negative 2.2 over 32, which I'm going to do a little bit of simplifying on that. I'm going to multiply both the top and bottom by 10 to get rid of the decimal there. So that's a negative 22 over 320. Then I'm going to divide both of them by 2 just to simplify it a little bit. So it's a negative 11 over 160, which is that slope. So it's minus 11 1/60ths x. If I put that in perspective, let's divide out. Oops, go ahead. Because I think that's just the echo in the system, huh? Okay. So that's 10.5 minus 0.069 x. So what this tends to be telling us is, what's this slope indicate? Remember, slope is a rate of change. What would that be indicating about our polar ice caps? Well, the negative would seem to be telling us that it's doing what? It is decreasing. It is shrinking. By how much? How much per year? Remember, it's in millions of square kilometers. So 0.069 is millions of square kilometers per year. So 0.069 million is about 69,000 square kilometers per year that it appears to be shrinking. Now, I will point out here one of the flaws in this data. This graph goes from 1979 to 2015, which is about 36 years. Seems like a long period of time, but 36 years in the lifespan of those polar ice caps is a relatively small period of time. So over that period, you can take almost any set of data. If you have points, I'm just drawing random points here to illustrate a graph. If I looked at that graph, would you say that it looks like that is increasing or decreasing over time? I'd say it's pretty steady over time. I mean, there's some variation, but it is pretty steady, right? If I drew a line through it, it'd be relatively flat. However, if I took and just put a window around this section right here, what would you say about it in that little window there? Definitely looks like it's decreasing. But if I put a window around it right here, it's definitely increasing. One thing that I caution, I don't want to get into a whole environmental science discussion, but in nature, things tend to go in cycles. And if you look at your temperature throughout the year, starting from January, February, March, and on through December, the temperatures tends to dip, rise, and then dip. And then as you keep going into the next year, it does the same thing. We have this cyclical nature. In natural phenomena, we have that cyclical nature. If you were to graph the average annual temperature each year from what we have from geological data over the last several thousand, even millions of years, that annual temperature would look like that. So it's the same type of thing. If I happen to take a window right here, it looks like it's going down. If I take a window right there, it looks like it's going up. If my window included the whole picture, well, it looks like it's just natural variation and staying relatively flat. So there's a big thing in statistics about what window you choose. I feel like in the last couple of weeks, I've done a lot of preaching about how statistics is used to lie to you. And it's actually very true. Statistics can, if you're not very careful, statistics can be used to be very deceiving. Okay, well, let's move on then to S5 for today. Any questions on, oops, go ahead. Sure, let's do that. It's 11:05. Let's do 11:10. We'll start up again. Take a look at S5. So for S5, what we're looking at here in problem situation 1 is looking at average temperatures in New York City, and we're looking at average temperatures in July again. So let's get down to that graph so I can pull it into the document here. So this is the graph we're looking at. So this graph here, that was a horrible paste job. I didn't get a move from it. It'll work. So for this graph here, we're looking at the average temperature in the month of July in New York City. So just as we were doing in the PNL, they want us to look at that and ask, do you see any trends showing in that graph? And if you do, what are the trends? So I want you to take a look and take a minute and look at that graph and think about, does there appear to be a trend? Does it appear to be going up, going down, staying flat? And then what about the data makes you think that it is doing that? Okay, so what do you think? Is the data going up, going down, staying flat? It is scattered. Do you think there's any general long range tendencies? Okay, yeah, so we're looking from 1960 to 2020. And remember, this is just the month of July each year. So they're taking into account the seasonal, and it is the average for the whole month of July, the mean for the whole month of July. As I look at this, you might be able to make an argument for a slight rise. And one of them basing that argument on is you can see this graph is lined up with the top of the page. It isn't crooked at all. So if I look here, drawing a line across at the very top of the page, I can see back in 1860, there are no points that are even close to hitting that line, whereas up here in the 2000, 2010 range, there are points that are getting really close to it. If I do the same thing on the bottom end, let me draw a line across, use the top of my page to draw a line across there. I see a similar thing. over here on the left side, there are 3 points below the line and 1 or 2 points that are touching the line. On the right side over here, there's just this 1 point that's kind of near the line or touching it, no points below it. So you might be willing to make the argument that there are lower lows in the late 1800s and higher highs in the early 2000s. But how would we quantify that? Well, one of our strategies for quantifying data is to break it into chunks and compare it. Now, with only 2 of you here today, this makes it would have been difficult with all 4 of you here. But with only 2 of you, it makes this a little more difficult. But what they've done here, if you look at, after these first 2 questions, it has a section there that says comparing distributions. And it gives you the data for 1871 to 1880. So for 10 years. And it wants you to find the mean for that set of data. In fact, it wants you to find both the mean and the median. So this is actually the next, it's after the graph, there's a table there. And I'm going to actually pull up Excel so that we can arrange this in Excel a little bit. So we have here for the 1871 through 1880 table. In 1871, it was 72.3, 77.5, and 72, 73, 75.4. Now you can see there's a lot of up and down from year to year here. And 74 is 73.9, 74 exactly in 1875, 79.4, 75, 77.8, 75 in 1979, and 74.9 in 1880. So those are the temperatures given in that table. Let's find the mean. The mean is found by adding them together and dividing by the number there. So how many numbers are in this list? 10. So what that means is in statistics, we talk about n. N is the number of items in the list. So that means that n equals 10. So to find the mean, we are going to add them all up. 72.3 plus 77.5 plus 75.4 plus 73.9 plus, plus 74 plus 79.4 plus 75 plus 77.8 plus 75 plus 74.9. So we added them all up to get 75 or 755.2. And of course, we are going to divide by 10. So that's going to equal 75.52 is the mean. So the mean temperature during that period of time is 75.52. Now the median is a little bit trickier. We'll talk about the median in just a second. What I want you guys to do for 1921 through 30, I want you guys to go ahead and find the mean there. So take those 10 numbers, add them together, and divide by, there's 10 of them, so divide by 10 to find that mean. And we'll talk about that in just a second. So if we look at these numbers, we went from 75.52 in the 1870s. We actually dropped to 74.98 in the 1920s. In the 1970s, we went up to 76.98. And in the early 2000s, holding steady or dropping slightly to 76.5. To give you guys a little bit of history, by the way, in the early 1970s, which was before my time, there was actually worry about global climate change, but they were worried about global cooling. So if you look at it from the 1870s up to the 1920s, it appears the temperature may have been showing a drop. So that was a concern at that time. It wasn't until the late 1970s, early 1980s that focus switched to being possibly global warming instead of global cooling. What it may come down to, and I'm not a climate expert, is that natural cycles again that we talked about. Okay, so the mean is one way of finding the center of data. We mentioned that data tends to make that bell curve. If we put those dots on that number line, that dot plot, and just drew a curve through the top dot in each column, we get that bell curve. The mean is one of the ways to measure the center of that. Another is the median. To find the median, we have to first put the numbers in order. From smallest to largest. Second is to find the location of the median. Which is just going to be in the middle of the list. And there's a couple of different ways we can find that location. So let me first take our list. We are back to that 1871 through 1880 list. And let's put those in order from smallest to largest. It looks like the smallest is the 72.3. Next would be, looks like 73.9. Say 74.9, 74 flat. And then a 74.9. I'm seeing two 75s. That's 1, 2, 3, 4, 5, 6. Next, I'm seeing a 75.4. Should be 3 more that I need. I need a 77.5. A 77.8. And 79.4. So those are the temperatures put in order from smallest to largest. Now with a small data set like this to find the median, we could actually just cross off the smallest and the largest and work our way into the middle. So as we cross off the smallest and the largest, one of two things will happen. Oops, crossed off the wrong one there. Either we'll be crossing them off and we'll end up with one number in the middle, which would be our median, or like in this case, we ended up with two numbers in the middle. If there's two numbers in the middle, the median is between those two numbers. Obviously, because there was an even number of items, there's 10 items in the list, there's going to be those two numbers in the middle. Well, between 75 and 75, if it's pretty obvious it's just 75, but technically you should add them together and divide by 2 to get that the median is 75. If this were a larger list, if there were a couple of hundred numbers in this list, you wouldn't want to have to cross off the smallest and largest. So to find the position of the median, you would take 0.5 times n. Remember, n is 10 here, so it's 0.5 times 10, which gives you 5. If the number you get here is a decimal, you would round up. If it's a whole number, which is what we have here, then it's between that place and the next. So that number came up to be a 5. That's telling us it is between the 5th and the 6th number in the list. If that number had come up to be like a 7.5, it come up to be a decimal, you would just round up to 8, and the 8th number in the list would be the median. So since all of these sets have 10, the median is going to be between the 5th and 6th spot in each list. So we've got a median here of 75 for the 1871 to 1880. I want you to quick find the median for the 1920s, 1921 to 1930. See what you come up with. What'd you get for the median there? Okay, 73.6 and 75.1. So you're going to add those together. 73.6 plus 75.1, then divide by 2, right? Perfect. That would be your median. How about for, let's do 1970 to 1980. $75.3. So that would appear to be a slight increase there again. And then let's do it then for the early 2000s. So it looks like a big rise there. Now, one of the reasons why the median and the mean might be so different in the early 2000s is there were a couple of really low points like the 72, and that'll cause the mean to change way more than the median will. So that's mean and median. Those are some, like I said, those are some measures of center on this distribution, that bell curve. The next thing we want to talk about is how do we determine how wide that bell curve is? Well, the width of that bell curve comes off of something called the standard deviation. So we're going to look at one set of numbers here and do the standard deviation. So I'm going to take the numbers for I'm going to go back here to 1871 to 1880. And I'm going to actually write the numbers vertically here, and I'm not going to have them attached with their number because I'm going to, well, I'll show you here. 72.3, 77.5, 75.4, 73.9, 74, 79.4, 75, 77.8, 75, and 74.9. So we have those numbers. The first step, step one in finding the median, or finding the standard deviation, sorry, is to find the mean. Well, we already found the mean of these numbers, and that mean was 75.52. Step two is to subtract the mean from each number. So that means I'm going to subtract 75.52 from each of these numbers. So you notice some are negative, some are positive. These are what are referred to as the deviations. That is how far each number in our list is away from the mean. If I were to add these up, by the way, down here, this should add up to 0. It gives us 10 to the negative 14th, which is 0. There's something wrong in the algorithm calculating the sum there a little bit, but it should add up, it does add up to 0. Step 3 is to square each deviation. So we take this number here, it's going to give us something called the squared deviations. We take this number here, the negative 3.2, and we square it. Now, when you punch that in your calculator, you often have to put it in parentheses so that it will square the negative as well. When you square something, your result should always be positive. The deviation tells us how wide this curve is, this bell curve. And once you know the standard deviation, there are a lot of other things you can do to analyze the data. We'll learn about later today, well, probably not quite later today, but on Wednesday, we'll look at a lot of different ways to use that standard deviation to analyze our data. It actually tells us a lot about the data once we know it. Step 4, add up the squared deviations. What that means is we're going to find the sum down here of these things. So we add those all up. Step 5 is the tricky one. Divide by n minus 1. For this data set, n equals how many? n equals 10, right? So n minus 1 would equal 9. So that means we are going to divide by 9. This, by the way, is what's called the variance. Step 6, the final step, square root the variance to get the standard deviation. So we have to take the square root of that, and that is the standard deviation. So that's a lot of steps. For this first set of data, the standard deviation is 2.11, 2.12, we would say. So from the 1870, 71 to 1880, what that is saying is on average, the temperature for that year is about 2.12 degrees away from the mean for that 10-year period. So the mean was 75.52. On average, any temperature for any individual year is 2.12 degrees away from that mean. For step 6, to do the square root, all that is this right here. We're taking. Okay. Well, the only way I can think of to say this for step 6 is to take the square root of the result from step 5. Now, since this is such a long process, I am going to go through one more example with you. So let's do the 1921 to 1930 here again. I'm going to get the temperatures in here, 77.3, 73.7, 73.8, 74.1, 73.6, 75.1, 74, 75.9, 75.9 again, and 76.4. So we have those temperatures all listed. What is step 1? Okay, we found the mean for these numbers. What was it? It was 74 point something. 74.35. So that's what we're going to subtract from each number here. So what is this column here? As we get these results, what are these called? Those are called the deviations. So that was step 2. Subtract the mean from each number. What's step 3? Square each deviation. In other words, square the result from step 2. These are the square deviations. So we're going to square each of these. Again, if they're negative, make sure you're putting them in your calculator in parentheses. Any number squared has to be positive. What's step 4? Yes, we're going to add up those results from step 3. So we've got the 19.745. What is step 5? Perfect. So n is what in this set of numbers? 10. Yes, there are 10 numbers, so n equals 10. So n minus 1 equals 9. So we divide by 9. And of course, that is what we would refer to as the variance. If you're ever asked for variance, that's what they're talking about. What is step 6 to get the standard deviation? Take the square root of that result of step 5. Let's take the square root of the variance. In Excel, that command, by the way, is SQRT, square root. So we get 1.48 is that standard deviation. So what that is telling us, we had a 2.12 is the standard deviation for the 1870s, and a 1.48 is the standard deviation for the 1920s. That's telling us that the numbers in the temperatures in the 1920s did not vary as much. They were closer together. On average, they were 1.48 degrees away from the mean. So I want you guys, I'm going to give you a couple minutes in your notes. I want you to find the standard deviation for the temperatures in the 1970s. If we look at these, the standard deviation has a lot to do with our margin of error. When we go to create that margin of error for any estimate, any interval estimate, that standard deviation is part of what works with that confidence interval to tell us how wide, what that plus or minus has to be, how big that margin of error has to be. So in this case, which decade would have the largest margin of error? You got it. That would be the largest margin of error. I'm just going to do capital ME for margin of error. And then, of course, the smallest margin of error, perfect. And again, that standard deviation is not the margin of error, but that is one of the numbers that goes into finding the margin of error. It still gets adjusted by the sample size and the confidence level and all that stuff. But we could tell that 1920 to 1921, 1930 is going to be the smallest. So that average there, that mean of 74.98 degrees, chances are the real mean is pretty close to that. Okay, so then the next thing we want to look at is we want to look at other ways of organizing this data. In fact, let's do this. Let's look at the table here. The largest standard deviation that we got was right here in this 2001 to 2010 area. Notice I put we have boxes around the decades that we calculated. This was the 1871 to 1880 right here. This one is the 1921 to 1930. This one here is the 1971 to 1980 versus the 2001 to 2010. Looking at those boxes, Without looking at the numbers we just did, could you tell me which one appears to have the largest, the most spread out set of numbers? Yeah, the 2001 to 2010. So does that make sense that it has the largest standard deviation here? Yeah, very much so. So now looking at these numbers here, going back, which would you predict going back would have the smallest box, the least spread out numbers back on that scatter? Perfect. And as we go back, we can see that really is the smallest box, in fact, much smaller. So those points really are less spread out. So one of the arguments that people would make against global warming right now is not, even though there might be a small tendency in rising temperature, they make the claim that, well, the variance, the standard deviation in temperatures is much larger. Temperatures are more scattered out both on the high and low ends of the temperature scale. So how can we claim that it's just getting warmer? In fact, if you go from the 1971 here, if we trace that box straight over, this one actually goes further below it than it does above it. So if we compared that box to the box from 2001 to 2010 to the box created in 1970s, it looks like it's dipping down further than it is rising up above it. So there's a lot of different ways that we can analyze this data. So the next way that we're going to look at analyzing this data is we're going to look at making a histogram. What they did in this histogram here is we took the numbers from 1969 to 1869 to 1898. And I'm going to make this a little bit larger for you here. At least I hope I'm going to make it a little larger for you. There we go. And what you see here is they took those 30 temperatures and they grouped them together. They said, okay, how many years is that average temperature between 70 and 72 degrees? And technically they probably had to do it as 70 to 71.99 degrees. And what they found is that there were 2 years where the average temperature in the month of July was in that range. And then they went from 72 to 74 degrees, again, probably 72 to 73.99. And they found that there was 9 years in that 30-year span that the average temperature was between 72 and 74 degrees. From 74 to 76, there were 11 years. From 76 to 78, there were 5 years that the average temperature was in that range. And 78 to 80 degrees, there were 3 years where the average temperature was between 78 and 80 degrees in the month of July. So this is the temperatures, the average temperatures down here. And then the height here is how many years the average temperature fell into that range. Any questions on that graph and what it means? Okay, so that was from 1869 to 1898. Next, they did the same thing starting at 1987, going to 2016. So again, there was 0 that went from 70 to 72 degrees. Remember up here, there were 2 years that the average temperature was between 70 and 72 degrees. From 72 to 74, there were 4 years that had that average temperature. 74 to 76, there were 6 different years that the average fell in that range. 6 years that the average temperature was between 76 and 78. There were 10 years where the average temperature was between 78 and 80. Now, if we look up here, there were only 3 years where the average temperature was between 78 and 80. And there were 4 years where the average temperature was between 80 and 82. Whereas up here, there were no years where the average temperature was up in that range. So if you were just looking at these histograms, Do these histograms show evidence for or against global warming? Do they against global warming? So remember, this is the 1800s here, 1869, 1868 to 1897, right? 69 to 98. And this is, do these temperatures in this graph look like there's more in the higher end? You're going the other way? Gotcha. This is just the frequency. This is the number of years that the average temperature fell into that range. So this is the higher temperatures right here. So if you look, in the 1800s, there was none of them that fell into the highest range. In the late 1900s, early 2000s, there were 4 that fell into that range. So if you looked at these tables, it might be tempted to say that is pretty strong evidence in favor of the average temperature has risen. But now, if somebody tried to use these tables to make the point, to try to prove to you that the average temperature is rising, can you think of any arguments that you might make against that, to refute that? What is being shown? What are these numbers that we put on this table? Where did they come from? What do they represent? Perfect. The average temperature in July. And we saw on that previous table that not only is there the average temperature and the high temperature, but it appears to be the range. Here it was going up and down way more than it was here. So the argument might be made that even though the average temperature in July seems to be way higher now than it was 130 years ago, well, not 100, but 110 years ago, the question would come up, well, what about the low temperature in January? If the low temperature is also increased, well, then maybe that is strong evidence for an increase in temperature, the global warming. But if that low temperature has gotten smaller, all that really shows then is that the range of temperatures throughout the year has started to be a larger range rather than an actual increase. Because if you go back to that standard deviation, starting in the 2000s, that standard deviation got a lot larger. So that's saying the temperatures are fluctuating a lot more now than they used to. Any questions? Okay, so doing that standard deviation calculation is one of the things that you are going to practice in your homework today. We're also going to be looking at, in the next couple of days, looking at things called z-scores and empirical rule. There's something we haven't talked about yet, but what these talk about, the z-scores and the empirical rule, what they do is they show how that we use the mean and that standard deviation that we calculated to analyze data, analyze and compare. So on Wednesday, we'll be doing a bunch of examples of the we'll talk about what z-score and empirical rule are, and we'll do some examples of where they're used so that you can see how they're used. And then that will wrap up our new material for the semester. So next week, Monday, we'll be doing a review, and then we'll be looking at taking our final test. Sam, have you been able to gather up your homework assignments and stuff so you can get them scanned and sent to me? Okay, perfect. So for class on Wednesday, of course, due Thursday, we have the OCE then for S5, out of class exercise for S5, and the practice for next lesson, PNL for S6. Those will be due Thursday. Then, of course, due from last class, it'll be due tomorrow, Tuesday, is we have the out of class exercises from S4, and then the PNL for today for S5. This PNL for S6 will be our last PNL of the semester. So then we should be just one more out of class exercises and we're done with homework for the year. Okay, we're a little bit early, but I'll let you guys out of here. We'll see you on Wednesday. You bet. Have a great day.